to see it being useful early on a lot, okay? Because we're trying to build skills, all right? For instance, if you play a sport, you go to the weight room to get faster, to get stronger, stuff like that, right? But a lot of times in a sport, you don't do those activities on the soccer field or the football field or softball field or whatever it may be, okay? So if I'm, in a weight room doing squats or something like that with a bunch of weight on my back, am I going to go do that in the middle of a soccer game? No, but you're building your body to do that thing, right? Okay? And when you go out to soccer practice and you're dribbling the ball around and you're, I don't know, I'm not very good at soccer, so whatever, but I don't know what you guys call it, but dribbling the ball around, doing skill, or doing individual drills, in a game, you might not ever do that individual drill again, right? Okay? But every once in a while, you might be put in a situation where that individual skill that you're trying to develop inside that drill and practice becomes beneficial to you, right? So mathematically, when we're doing these proofs that really doesn't seem like the truth is really important to us, we're developing a skill so that when we see it inside another proof that is beneficial, we have the ability to use it as beneficial to us. Does that kind of make sense? Okay? And that's early on in your mathematics experiences in high school, you're going to find out that a lot of things that you do are building skills for larger problems. Okay? Everyone always asks, well, where am I going to use this? What's this useful for? There's a lot of times that directly you won't. Okay? But you're building a skill so that you can be better at another style of problem or be better inside another problem that makes you do that type of thing. Okay? So just for an example, you guys might deal with like solving equations that look like, let's see if we can pull one up here, like an equation like this. Okay, 1 over x plus 1 over x plus 5 equals 1 over 8. And you go through and say, okay, I can learn how to solve that, but where is that useful? Okay? Am I ever going to use that in the real world? That problem directly? Probably not. Okay? But you guys remember the question that you saw in Algebra 1 where it says, Timmy takes an hour to mow the lawn and Sarah takes an hour and a half to mow the lawn. How long will it take them to mow the lawn if Timmy starts at 12 p.m. and whatever the girl's name was starts at 12:45? Okay? You've seen questions like that, right? Okay? That's where you would use that tool of being able to solve this equation. Okay? Because those types of called work problems, and every work problem will incorporate or keep this concept intact. You don't have to be able to solve an equation like that. Or if I'm thinking about, maybe you have a swimming pool at home or something like that, you want to think about kind of cleaning it out or whatever. I don't know why maybe you would do this. Maybe it's the bathtub. Leave the water on the bathtub. It overflows, right? Okay. But leave the drain open. Turn the water on. Turn both faucets on. This is still going to overflow. You got water leaving, but you got water coming in too, right? And most of the time, the water coming in is coming in at a greater rate than when the water is leaving, right? So you can set up an equation that's going to allow you to solve and figure out how long can I leave the drain open and the water on, both faucets, and come back and still have a dry floor. Okay? So that might be a real-life application. I'm not sure why you maybe want to know that right off the bat. But you're building skills in courses to deal with other problems. Okay? And that's really what we've been doing so far with some of these proofs, is to develop skills for something like what we do today. Okay? Because today we're going to come across our first theorem. Okay? A theorem is simply a conjecture or a statement. Okay? Conjecture basically saying that it's a true statement, okay? A true argument, but it's one that we can prove. And that's different from what we've learned about postulates. Postulates, we had to take the person's word for it, right? Okay? We took the author of the book says this is true, so we just agree with it. We can draw pictures and get an idea of, yeah, it makes sense. But a conjecture or statement that you can prove is called a theorem. And throughout the book, pretty much every section we come across after this is going to be talking about specific theorems. Some texts or some sections have one theorem. Like this one only has one theorem. some have 6 theorems. Okay? But every theorem we come across, we should be able to prove using those skills that we've developed in the proof process so far. Okay? This first theorem says that we call it the vertical angles theorem. Okay? Not every theorem is going to have a name to it. Okay? The ones that do have names are nice because instead of writing out the entire statement in our proof, we can just write the name of it. Okay? We got to know what's inside that statement if we just do write the name of it. Do not ever remember, and this goes for any math class, do never remember a theorem by its label, like theorem 2.1 or something like that. Because in this book it might be 2.1, but in another book it might be 3.1. Does that make sense? Okay. So you can only do that if you know what book you're referencing 2.1 from. Most people aren't going to know that. First theorem says vertical angles are congruent. I think the textbook does a terrible job here in kind of realizing what they've set us up with in regards to conditional statements, and they have a perfect opportunity here for kind of like a teaching or learning moment, and they don't do it. Okay? Let me just wipe that stuff away real quick. What I mean by that, we've been dealing with if-then statements for a while now, right? Okay? They have the perfect opportunity to provide us our first theorem in an if-then statement, but they don't do it. Okay? So let's rewrite this and say, if two angles are vertical, then they are congruent. Okay? I think the text would do you a little bit more justice if they would write it that way, because we're going to try to prove this theorem. And what I want to do is go through kind of an exercise that allows us to set up information in regards to proving a theorem out of the textbook. Because you're going to come across at some point, whether it be this class or another class, where they write a theorem out, and one of your exercises in your homework is, I go back to section 2.1 and prove the vertical angles theorem. Okay? Well, that's all they say. They don't give me a given information. They don't give me a proof information. They just say prove the theorem. So we have to be able to take this statement, pull it apart, and come up with the given and the proof on our own. Okay? And I kind of talked about this, and I'll show you that information here again in a moment. I deleted it, but yesterday we talked about the if part. Okay? The if part in any if-then statement is what you know to be true. Does that make sense? Okay? If you have two angles in front of you that are vertical, okay? If that is happening to you, if that's the given information, okay? So our given information, two angles are vertical, okay? If you know that's true, the prove information is the conclusion. All right? So the hypothesis is your given, and the conclusion is your proof. Okay? Now, what's kind of problematic about the way I wrote that is we would like to have a picture, and we would like to be able to talk about those two angles. Okay? So if I'm going to talk about those two angles and reference them, they need names, don't they? Okay? So what we do is we provide a picture with specific names. Okay? So I want to look at just the picture they provide me up there. I'm just going to say, instead of writing two angles are vertical, I'm going to write angle 1 and angle 3 are vertical. Does that make sense? Okay. Still says two angles are vertical, but now I have angles that I can actually talk about. Okay. I could have also used 2 and 4 if I wanted to. Prove they are congruent. Well, the statement that they are congruent would look like this. Angle 1, congruent to angle 3, and obviously that has to be the congruent symbol. I don't have that on my keyboard. But that's what we would start with if we wanted to prove this theorem true. All right? And then angle 1 and angle 3 are just arbitrary angles. They could be any measurement they want to be. But we're going to find out that if they're vertical, their measurements end up being the same regardless of whatever one of them started out at. Okay? So that's where we get to the next slide. The next slide says we're going to prove this, and you don't necessarily see this statement here. Okay? You see that statement there in the next slide. Okay? So we're going to walk through and prove that statement. What we need to realize as well is that when we prove a theorem, you don't know it's true until you're done. Okay, I do not know that angle 1 and angle 3 in this case are congruent, okay, until I'm all the way finished with the proof. Okay? The idea of if I'm trying to define a word, and you've maybe come across this, if we try to define a word, or I don't know a word and I look in the back of the book, or I look in a dictionary, some really poorly written definitions use the word that we're trying to define, don't they? Okay? Somebody, yesterday we were talking about dependence, and I asked, what does dependence mean? And they said it's when you depend on something. Well, that's kind of a bad definition for dependence, isn't it? Okay? It uses a derivative or a format of the word I'm trying to define. So I cannot, if I want to prove vertical angles are congruent, then I cannot use that statement inside my proof. All right? Because I don't know it to be true yet. That's what we're trying to show. In the past, I get people say, well, you just told us vertical angles are congruent. That's what they're trying to get me to prove here. So I just write step 2, angle 1 and angle 3 are congruent because vertical angles are congruent. We don't know it to be true yet. That's what we're trying to show. Does that make sense? And that's going to be a task throughout the year. Whenever we see a new theorem, some of them are trivial. We won't spend a whole lot of time on proving them. But the ones that are really important, we will spend time proving them. And we use all the information that we learned prior to that theorem to prove it. Okay? Once we prove it, then we can use it. Okay? My voice, I don't know if I lose my voice or puberty or whatever, it keeps screwing up on me. All right, so I cut and pasted this one out of our textbook, and I think it does a pretty good job of covering what we need to cover. There is one step between 4 and 5 that I wish they would have added. The author doesn't think it's necessary. We'll talk about how we could change it a little bit to maybe make it a little bit more precise, a little bit more accurate, because you might see this step on a end of course exam and really not know why they're doing what they're doing or anything like that. So I want to make sure that we do it eventually talking about that. Touchscreen is phenomenal again. All right, so we start off with the fact that angle 1 and angle 3 are vertical angles. Okay, they want us to prove then that they are congruent. So that is the theorem we just learned. Obviously, the first statement is given. Okay, this is the one, and you're not going to see it too many times. Okay, but that is the one time that we get a vocabulary word in our given that we're not going to reference and use, okay? Because what that vocabulary word does, it's basically just, it's almost like an existence idea. It just shows you how vertical angles are made, all right? And if you remember the definition from, I don't know what section it was in chapter 1, but it said vertical angles are angles in which the rays of that angle form opposite rays of that angle. So it just shows me how angle 1 and angle 3 are formed off of one another. Does that make sense? Okay. The use of vocabulary in that set of steps that I gave you in the PowerPoint the other day, there's 7 steps. Being able to recognize a vocabulary word, a lot of times it's going to provide me a congruency statement or a summation or something like that. Vertical angles don't do that. Okay. Knowing that definition, nowhere in the definition to say these 2 angles have this relationship or these 2 angles add up to this or anything like that. So it's one of the few times when we see a vocab word, we kind of neglect it in our statements of it. Okay? So we go through, we draw everything in our picture that we know based off congruencies out of the given. None of that stuff was given to us or provided, so we skip that step. Vocabulary, we can skip that step. We get to the step where we have to look at our picture. And looking at our picture, hopefully gain some information, gain some ideas about our picture. One thing I wanted you guys to realize, this isn't always true, but a lot of times, if they label angles in your picture or segments in your picture, they want you to talk about them. Okay? So for instance, they don't give me anything about this angle down there, right? I'm probably not going to talk about that angle. They do tell me about angle 1 and angle 2. They label angle 2 and angle 3, so I probably want to talk about those things. Does that kind of make sense? So it's kind of a guide maybe to realize what do I need to look at and reference in this proof. When you look at this, okay, you've got some angles, and I want to look at those two angles right there. Angle 1 and angle 2. What do they form? What type of shape, if I put those together, they form that thing right there? And what is that thing? That's a line, right? Okay. Now these were angles. These were angles, and there's two of them, so it's a pair, right? A pair of angles that form a line are referred to as what? A linear pair. Okay. Now, if you remember, back to, I think it was like section 1.8, something like that, it said a linear pair is a pair of angles that are supplementary. Okay? Sorry, a pair of adjacent angles whose non-common sides form a straight line, and then we came across that and said, well, that means that they must be supplementary. Okay? So they have to be adjacent angles that are supplementary. That's what a linear pair does. Does that make sense? Okay? So we've got angle 1 and angle 2. They're adjacent. They form that straight angle. So 1 and 2 must be supplementary. That logic is all wrapped up in what we call the linear pair postulate. That's the reason why we can make the argument that they're supplementary. Okay? Because visually, when we have two angles that are adjacent, form a straight line, they are supplementary. Okay? And that whole phrase is wrapped up in the linear pair postulate. Is that okay? We see that a lot. Okay? Through a lot of proofs that we do, we'll see one next week at some point where essentially those steps are all the same. From this proof to another proof to another proof. It starts to be very pattern-based kind of work that allows you to get through many different proofs and come up with many different truths eventually. The linear pair postulate. Now, the same thing happens for 2 and 3. Okay, they're a linear pair. They're forming a different line. They're forming that line right there. But it's the same logic, same reason, so that's why we've got both those statements. And this is the one reason. The next thing happens is that you just introduced a vocabulary word, right? What's the vocabulary word that you just brought into the problem? Yeah, but look at the vocabulary word that we're going to look at the vocabulary words that we bring in on the left hand side. So we brought supplementary in on our statements, right? Okay. We'll never. These are our reasons. That's kind of the dead end. Once we find a reason, we're done with that, and we're going to look at this stuff. Okay. So this is the new vocabulary word that we've introduced. Every time there's a vocabulary word, we want to talk about what that means for us. Okay. What that means for those particular angles 1 and 2. If I look up the word supplementary in the back of the book, it's going to say there are two angles that what? Yeah, they add up to give you 180, or they sum to give you 180. Is that what we're saying right here? Yeah. Okay. Now, it's not as explicit as saying in words, it's two angles that add up to 180, but we have to look at that and say, well, that information in line 3, that first line, is coming because we know the definition of supplementary angles. We know that in the back of the book it says two angles that add up to 180 degrees. Okay? And for us, we just have to talk about which angles are specific to this problem. Is that the same logic, same argument for 2 and 3? Measurement angle 2, or angle 2 and angle 3 are supplementary, and then they make the argument that they add 180. All right? I would say 90% of the time when you have one pair, and in a lot of proofs that we do, if you have one pair of angles that are supplementary, you're going to have two pairs of angles that are supplementary. And the reason for that is because we want to be able to do something like this. We want to look at those two right there. Okay? Those two ideas right there. Remember yesterday there was a question that had like, I think it was RT and WY. We did a segment addition that said like RS plus ST is equal to RT. And then we had WX plus XY is equal to WY. But previously in the question, we had said that these two things were equal. I think it was RT and WY. We said those two things were equal. Okay? Well, if they're now 180, they're both 180, because it's just kind of paralleling off of a problem we've already done. If those two things are the same, Okay? What can you tell me about those two things? If I have an object like, if I have 3 plus 5, what's 3 plus 5? 8. What's 2 plus 6 give me? Gives me 8, right? So they both give me 8, right? So can I say 3 plus 5 is equal to 2 plus 6? Because they both give me 8 back, right? That's what we're doing here. If I've got these two things are something plus something is 180, something else plus something else is equal to 180. So that line of information, the 1 and 2 is equal to 180, 2 and 3 is equal to 180. But because they're both equal to 180, can't I say that those yellow parts are the same? Okay. So that's what we do. We say measure of angle 1 plus measure of angle 2 is equal to measure of angle 2 plus measure of angle 3. Does anybody know what that process was yesterday? Yesterday we had something that looked like, we said I think RT was equal to WX, okay? And then we ended up with RS plus ST is equal to RT. And we had WY, sorry. We had WX plus XY is equal to WY. And we had said, because these two things were equal, just like we just did with the proof we're doing, then those two things are equal, right? Okay? We did that proof yesterday, and what I want you guys to understand and recognize is that we're doing something extremely similar, if not the same, right here. Okay? The step yesterday was substitution. Okay? Because what I'm doing is I'm recognizing that I'm going to replace down here, and there's a couple different ways you can think about it, but I'm going to replace this 180 with what it's equal to. And I'm showing up here that maybe that 180 is equal to 1 plus 2. So if I interchange those two things, I get 2 plus 3 is equal to 1 plus 2, which is what this line here is saying. Or I can do it this way and say, I'm going to replace that 180 with what it's equal to down here. So interchange those two things, and then I get exactly what they had in line before. Is that doable? Somebody in the last class said, I'm going to do it this way. I'm going to write measure of angle 1 plus measure of angle 2 equals 180. And then 180 is equal to measure of angle 2 plus measure of angle 3. And then they merge those two things together. They put 180 and 180 overlap each other, right? Do the same thing. And that eventually gets them that argument that 1 plus 2 is equal to 2 plus 3. Do you remember what that process was called when we did that? That's transient. That's an A idea. There's B. There's B again. And then there's a C idea, right? A is equal to B and B is equal to C. Then A is equal to C. 1 plus 2 is equal to 2 plus 3. So if you wrote transitive here, that's 100% perfect final. Okay? The one thing, hopefully we all start to learn that, that's an acceptable, either one of those is acceptable, and then we get on Math Excel and they give us a drop-down window of 6 things. Hopefully we realize they'll probably only give me just substitution. Transitive won't be in there, because then there'd be confusion on which one to choose, or vice versa. Okay? If at any point, because there are times where it has to be substitution and it can't be the transitive property. But if that ever happens and you chose transitive, but it should have been substitution, voice that in class. Let me know. Let me look at it. We can talk about why maybe they're forcing it to be substitution, not necessarily transitive property or vice versa. But most of the time, I'll probably just give you the point anyways. And I think you're on the right track. They're very similar arguments. Okay. But sometimes we preference or prefer one over the other. Okay. Now, what I don't like about this proof is that they kind of glaze over a step. And some authors will do this. Okay. But you've seen this in algebra. You do this all the time. If I have 2x plus 5 equals 10, what are you going to do both sides? Subtract 5, right? Don't most people do this? Okay? So most people do that, but what you're really doing is you're telling me that what you're going to remove over here is identical to what you're going to move over here, right? Okay. You guys remember what the property was? It said if A, I guess they didn't say, it wasn't even written in the statement. I'm sorry, it was A equals A. Well, in this case, -5 equals -5. You guys remember the reflexive property in that video? Okay. The way I remember reflexive property is when I look in the mirror, I see my reflection, right? So my actual face and the face that's in the mirror, they should be the same, correct? Okay? And that's what we're seeing here. Maybe this is my actual face on this side, and this is the mirror. They are the same. Reflection, reflexive. Okay? Kind of go together. And that's what we want to do, really, in this problem here, is before we do anything, we want to say measure of angle 2 equals measure of angle 2. I'm going to call this step 4.5. 4.5. And I'm going to throw in the reflexive property. That's the logic or the reasoning. Okay? The reason I want to do that is just because of what we do in algebra. If I know that I'm about to subtract something from both sides, I want to tell everybody that's doing my work that those two things I'm going to remove are the same. And it's a lot more important, I think, here, because most people obviously are going to say, you know, if you skip this, if you just went straight to 2x equals 5, skip that stuff. Most people are going to argue and recognize, well, yeah, 5 was equal to 5 and remove it from both sides, right? Because I have that numerical quantity. But here, I don't have a numerical quantity for measure of angle 2. I don't know what that number is. Does that make sense? It's a hidden number being represented by measure of angle 2. That's simple. We want to just tell everybody, hey, whatever's behind that symbol of measure of angle 2 on the left-hand side, whatever that number is, it's the same number hidden behind that symbol right there. Okay? So that's the purpose of the reflexive property, is just to tell people what you are about to do, what algebra you're about to do. You're doing it because you're doing it for both sides of the same value. You're adding the same value to both sides, subtracting the same value, whatever. Okay? So now, 4 and 5, or sorry, 4 and 4.5 together help me get statement 5. Because basically, don't they just wipe the 2's away? When I wipe the 2's away, through algebra, what process is that? What math is that? Statement 5. You get rid of, we got rid of the same thing on both sides, right? What algebraic operation is that? When I say operation, you have 4 choices. Adding, subtracting, multiplying, and dividing. Subtract. Okay. So that's the subtraction property of equality. And that leaves you then with 2 numbers that we now know are equal, right? 2 numbers that are equal. And those numbers, with the notation that we're using there, represent angle measurements, right? Okay. Well, if those 2 angle measurements are the same, what does it tell me about the 2 angles that they come from? What can I do with them? Overlap them, right? And if I can overlap them, and they match 100%, they're said to be congruent, right? So we go from equality to congruence. What allows you to go from equality to congruence? We saw it like 5 or 6 times yesterday. Good. Definition of congruency is that last step 6. And now, what we've done, we started with, the only information we started with, that 1 and 3 were vertical, right? We used all the previous information that we know, supplementary angles, adding and subtracting, that kind of stuff, substitution. We use all those things together, and if we start with 1 and 3 being vertical, we gain the idea that 1 and 3 are congruent. Okay? Now, 1 and 3 were just arbitrary angles. We didn't specify that they had to be a certain type of angles except for vertical. So then, whenever I start with any other angles, whether they be, you know, if I look at angle 2 and 4, I should be able to make a similar argument now about 2 and 4 and see that 2 and 4 will always be congruent as well. Is that doable? Okay. So we have proven this theorem that vertical angles are congruent. And what's nice then is now that we've proven a theorem, we can use it whenever we want to. So from today on, if you ever see angles that are vertical in a problem, you can say that they're congruent. You know that fact. Okay? And it's going to maybe speed up the process of being able to identify congruency and help us learn a new truth. Okay? Because without this proof, okay, without this proof right here that we just did, okay, when we come to line or slide 4, we're eventually going to want to say angle 4 and angle 2 are congruent. But without the proof we just did, it would take 6 or 7 steps, however many steps that last proof was. Does that make sense? But now, to show 4 and 2 congruent, I say vertical angle theorem, and that encapsulates those 6 or 7 steps we just did. And it makes things a lot easier. Okay? So let's kind of work through this one. I want to work through this one, and it was proved by the last class that kind of what I wanted to happen. So I got a lot of answers and a lot of remarks that were kind of false, and I just want to make sure we draw our attention to those things and recognize why and why we can't say them, and when maybe it is appropriate that we could say them. But the first thing here is that this is given, right? Angle 1 is congruent with angle 4. So when you have explicit information given to you as a congruency, you go to your picture and you fill that information in. Okay? Now, are there any vocabulary words? No. So I skip that step. That's going to eventually get me down to having to look at the picture. Once you get past your vocabulary words, you always look at your picture. And you try to think about what you know about your picture, what you can argue about your picture. Okay? What is something, anything that you can think about, what we can argue about that picture that would be true? Okay? Where does it tell you that? It doesn't. Okay? It looks like they're all equal, right? Okay? But nowhere does it say 1 is congruent to 4, 1 is congruent to 2, 1 is congruent to 3, or 2 is congruent to 3, and 3 is congruent to 4, anything like that. We don't have that amount of information yet looking at our picture. Okay? Because right now, I know these are here, but right now we're viewing it, so we don't know those things. Okay? We don't know steps 2, 3, and 4, 5. If I look at my picture, last class said, well, angle 1 is 90 degrees, angle 2 is 90 degrees. And it looks that way, right? Does it say that anywhere? No. In words, it doesn't say anything about right angles or 90 degrees. And in the picture, it doesn't say anything like that, right? So that's information that they're trying to interpret that is not necessarily true. I'm not saying it's false, but I know it's not true. Okay? One class said, or I guess one group said that 1 and 2 could be supplementary. Would you say 1 and 2 are supplementary? We could go that route. Okay? I'm going to try to avoid going that route, but we could go that route. So if you say something that's true, that's awesome. That's fine. As long as it's true, you can write anything down you want. Does that make sense? Okay? But once you start saying things are false, then you got a problem. 4 and 2 are what? 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 Not adjacent. Vertical. Okay? 4 and 2 are vertical. Now, why is that useful? In the last proof, what did we say about vertical angles? They're congruent. So that's it. That's the situation. Like I say, angle 4 and angle 2 are congruent because of our vertical angles theorem. Okay, vertical angles theorem. So 2 and 4 are congruent. What about, and this is kind of because they're directing us on what route we got to go here. Now they say 1 and 2 are congruent. Okay? 1 and 2, if I look at them, we do have congruency markings in both of them, right? Okay? So I've got 3 things up here, and I'm picking out 2 that are congruent. What process is that? A property. It might be easier to look at it 1 as A, 2 as B, sorry, 4 as B, there's B, and there's C. This statement becomes A equals C, so then the transitive property. Okay? So we're looking transitive. Okay? And now I look at 4. And 4 says angle 1 is congruent with angle 3. Well, what types of angles are 1 and 3? Vertical. Alright, so vertical angles are congruent. Stating the vertical angles theorem. Okay. Now I draw that in my picture. And now looking at my picture, I've got 4 angles that are all congruent, right? So can you pick out any 2 that you want? And of those two of them are 2 and 3, right? So we haven't stated together yet. So that logic then is a transitive property here. Okay? And it's transitive because of these two here. Okay? That's not the best order, but we're saying maybe angle 2 is our A, angle 1 is our B, angle 1 is B, and then 3 is C. So A equals B, and B equals C, and then A is C gives me 2 to B 3. Does that make sense? If I did not have the vertical angles theorem, because this was, I think in the last slide, that was 7 steps, right? This would be another 7 steps. So this proof would be 8, so what, 14, 15, 16, 17 steps if we didn't have those two theorems. And that's the use of theorems, is to condense our proofs, okay? You can, as long as you find something that's true, you can write it as a theorem. But the use of theorems and the necessity of them is that we use them a lot. Does that make sense? So if I'm going to come across something that's true, but I'm not going to use that ever again, it's kind of silly and pointless to call it a theorem. Does that kind of make sense? Okay, so theorems are things, statements that we're going to use on a very heavily inundated kind of right? We're going to use a lot. Okay, so that's what we call it theorem. What? I want to do. You're going to see some of these in your homework. Something like this. Okay. Now that we have this theorem, guess what happens almost every chapter, every section we see a theorem. We then start to apply that and use that theorem and reinforce that theorem algebraically. Okay? So what can you tell me about this angle 3x and this angle 2x plus 40? What kind of angles are they? Vertical. So what's the relationship between their measurements? We should be able to say 3x equals 2x plus 40, right? And subtract 2x from both sides? X is 40, correct? Okay. X ends up being 40, so can I plug that back in to find that angle? What would it be? Careful. 120, right? This angle here is also going to be 120, right? Now, on test, even the end of course exam, they might ask you, they might label things, say that's angle A, B, C. Okay, so they might initially ask you, what is the measurement of that angle? Okay, well, people look at that and they say, before they start doing anything, they say, well, there's nothing written there. I can't do that problem. Okay, but you can use the context of the information around, right? If you're reading a novel and you don't know the word in the novel, don't you try to interpret that word by reading the sentences that are around it? Okay, so you use the context to find it out. So I look at the things that are around it. We see we got vertical angles, right? Okay. Once I know that 120, how does that 120 relate to that angle right there? They're supplementary. Good. So what's that ABC got to be? 60 degrees. Okay. And that type of question does several things. It tests you whether you know the vertical angle standard and theorem, and it also knows if you know linear pairs are supplementary. Okay. So it's 2 or 3 things there, but that one question can get at and understand and say you're good at this if you get it right. You know you're good at those 3 things. Okay. If you get it wrong, there's a disconnect somewhere on those 3 things. But that's the purpose of why you might see questions like that. That's one thing about this course when we start doing the algebra stuff, is that you don't want to force yourself into trying to, as quickly as possible, find the angle measure. Because you might have to do a little work around. You might have to move things around and do maybe 2 or 3 individual smaller problems to help you learn something about the questions we ask. Okay? And I think that sometimes frustrates people. There is an assignment in Math Excel. It's going to give you a handful of things like that. You're probably not going to be able to finish the assignment because there are some things about these theorems. Okay, so I'll leave that open beyond Monday. So once we talk about these, then we can finish that assignment. Right now, like I said, anticipate a test on Tuesday at the earliest, and I've opened up a chapter review. We'll talk Monday and then see where we're at. Yeah, kind of.
There are some possibilities